Very pleased this morning. Welcome, I should say. Welcome to the second day of ICFP. And I'm getting ahead of myself here because I am so pleased to introduce Pat Hanrahan this morning. The first time I saw Pat, he came to Utah to give a talk, a distinguished lecture, part of the series by the Scientific Computing and Imaging Institute. And they special forwarded the abstract to the department. I thought, well, it caught my eye because it talked about domain-specific languages. And I went to see the talk, and I really liked it. But I thought, why is the Imaging Institute hosting a programming languages talk? It turns out Pat is well known in graphics and visualization. For example, he was one of the founding employees of Pixar, and there he was the main architect of RenderMan. Now, the RenderMan shading language, that's the kind of DSL that gets you an Oscar for technical achievement back in '93. And in that same year, he also got the SIGGRAPH Achievement Award. And he kept working in graphics and got their highest award, it has a long name, Outstanding Creative Contributions for Graphics. That was in 2003. Meanwhile, he was working in visualization. That's not the same as graphics. They're related, but different communities. Again, made a big splash there with the domain-specific language. That was VizQL. And that turned into a company he co-founded called Tableau, which you probably heard of as well. And I'm skipping over all kinds of other awards and domain-specific languages. Not every language that he's worked on has turned into a multi-billion-dollar company, but still, when he says that he's interested in functional programming and DSLs for hardware design in this area, I think it's something we're going to be interested in. So again, I'm very pleased to introduce Pat.
Great, thank you. Can you hear me okay? Am my mic on? Yeah, well, thanks, Matthew, for the invitation to come and speak. It took him a while to talk me into coming here. I work in computer graphics. That's my main area. I've done some work in databases, and I'm starting to work in hardware. But I don't really work in programming language, but I think I'm sort of an amateur at it, or a serious amateur at it. So maybe I'll just talk a little bit about my background and how I got into the subject. So Matthew mentioned that I worked at Pixar, and that was my first job, and I was in charge of their rendering system. And all the artists and technical directors wanted some way to extend the system. So we had built the renderer, and in the middle of the system was some function that had to be called to describe how some surface looked, okay? So we call it a shading calculation or shading language. And so at that time, I was sort of, by the way, my background is in physics. I'm not even a computer science background. But I had known about Linux and Unix, and I know about little languages. So I built this little language, this is just a little piece of it, where I could describe how the light reflected off a surface. And so an artist could write this little language. This shows a particular reflection model, and we would compile that, download it into the renderer, and they could make pictures. And this is, surprisingly still used today. The other thing about other language I worked on, which he didn't mention, but I was quite proud of, was graphics is always performance limited, right? Because first of all, we have unbelievable amount of computation that goes into in every single image. A typical image at Pixar now takes about a petaflop to compute. It takes about 24 hours to compute. And every pixel takes more than 1 million to 1 billion flops for each pixel. And so you're always compute limited. And so that's why GPUs have become so powerful, right? We just have an incredible appetite for performance. And so what was happening in GPUs a little while ago was they were becoming these incredible parallel machines. They were multi-core, multi-threaded SIMD machines. Like, it was sort of unbelievable. Every form of parallelism that we sort of knew how to create, they were sort of implementing in this hardware. And so one of my students, Ian, built this system called Brook. It was a very simple system. It just took old ideas from data parallel computing, going all the way back to the connection machine and before, and just sort of built this very simple data parallel language. And then we built a compiler that would map it to a GPU. And so we basically just said, this is a general purpose computer, general purpose parallel computer. Let's try to use it for graphics. Now, it had a few warts, but it was an attempt to try to do that. And I remember at the time I said, why am I doing this? Like, you know, there's all these people that know way more about programming languages and about parallel computing than me. Like, why are we doing this? And it was really hard. I talked to all sorts of people to try to get them to work on this problem, and they just weren't interested in it. They didn't really believe the GPUs were going to be very useful. They didn't really like parallel computing. The idea that you'd have to do SIMD and multi-threaded and multi-core all on the same machine was sort of antithetical to most of the people because they were all interested in one particular model of parallel. So I sort of had to do it, or Ian had to do it. And that's sort of the story of my life, I think, is I just various times these problems come around, and I've always been interested in trying to take like a programming language approach to solving them, which was sort of the point of my talk, was, you know, it's just, you know, I knew enough about programming language that I would try to build a language because the language would be much more powerful than just a simple library. Another application I worked on, sort of quite different, was visualization. But let's say you wanted to make, you know, this kind of visualization of some election results, polling results, two side-by-side maps. I built a language called VizQL for doing this. So this was a very different kind of language in that this was sort of based on SQL. If you know SQL, you'll recognize this. But it was sort of a merge of SQL, which specified a query, with sort of the graphics, which specified the visualization. And so with a very simple, you know, specification like this, you could both generate the query, which would compute the sum of the amount broken down by these zip codes and so on, and then display it as a map with these circles. And you can sort of see it's a very simple, intuitive language. And again, that turned out to be really useful because now we could compile these queries to various types of databases, high-performance databases, and the back end of this was actually a very high-performance database which would try to do these queries quickly and format that picture. So anyways, that's sort of, at least that's whatever credibility I have, I would describe it. I'm not really a language person. I'm listening to the talk. I have trouble following a lot of functional programming, but I'm sort of a serious amateur. And I like to apply language ideas to new problems. And I thought I'd talk about today is what I'm working on now and how I think maybe another plea for help. When I was working on data parallel computing, I made a plea for help. Maybe some of you can help me solve the problem of how to build hardware. So that's what I'm working on now, how to build hardware. And so you might ask, like, why would I be interested in doing this? Well, I always interested in hardware because in graphics, we want fast hardware. But, you know, some people say, well, why now? Because aren't we sort of at the end of Moore's Law, right? You've all heard about this, the end of Moore's Law. But, you know, here's a plot of, you know, Moore's Law, transistors doubling, number of transistors on a chip doubling every 2 years. And you see it starting to taper off there. I was just noticing, I just grabbed this picture, the Apple A12 processor just came out. And that's a processor with 6.9 billion transistors, 7-nanometer technology, sort of the first big 7-nanometer chip. But that's the scale that we're at now. But 7 nanometers is pretty small. And you've all heard about this, that, you know, Moore's Law is ending. Or really what that means is CMOS device scaling is ending. And it was hard to get that 7-nanometer chip out. People think they'll go to 5 nanometers pretty quickly, or not, maybe, you know, a couple years. But whether they can go to 3 nanometers or 1 nanometer is actually somewhat uncertain, as far as I can tell. I've talked to all the vendors. And, you know, the reason basically is that, you know, one silicon atom is 0.21 nanometers. So eventually you just get down to like a transistor like is going to be a couple atoms, and it's just, you know, it's just sort of impossible to build a transistor out of a couple atoms. Now, you could switch to another technology. You know, you've probably heard of carbon nanotubes, but nobody really knows how to do that. So, you know, at least Moore's Law, which was about CMOS device scaling, is ending. So this would seem to, well, first of all, this is sort of disconcerting if you're in computing, right? Because we've had this free ride with Moore's Law. So that's a little, you know, worrisome. But, you know, we still have a lot of transistors to work with, so maybe that's not so bad. Anyway, that's the first thing. Okay, end of Moore's Law, interesting point in time. The second thing I want to spend a minute on this is what's called Dennard's Law. And this is about physics. And one thing I do want to say is that most of computing, if you build hardware, is about physics, not math. Because what you want, your only model of your only cost model for computation is how much energy you use. And Dennard's law is sort of an example of that. So this sort of says that as you make transistors smaller, okay, X is how much you scale it, so you make them half as big or something. Then you can also scale the voltage down. You can scale the voltage down because the electric field is the voltage divided by the distance, and so if the distance gets smaller, you can keep the same electric field. Then the capacitance goes as that scaling factor, and the energy goes as CV squared, so that actually goes as that scaling factor cubed. It turns out that if you make things smaller, you can run them faster, because they take less time to, okay? So the time, so you can do calculations faster. That's one reason as Moore's law was going on, the computers just kept getting faster. And you get more transistors. So if you take the area times the time to do a computation, which is sort of like one switching event, okay, that also goes as x cubed. So if you take the total energy divided by the total area and time of a computation, you get 1, which is truly amazing. That meant every time they made the chip smaller, it had the same power density, okay? And that was critical because, you know, you could not keep adding power to a chip. And so this is called Dennard's law. And this says that as we scale the technology, it's isopower. But this is no longer true. And this has happened actually already. So what happens is once you get down to a certain size, you can no longer keep lowering the voltage. I'm not going to go into all the details of that, but you can no longer lower the voltage. It's already happened. Done. They don't lower the voltage. So that means all current designs, all chips built are power constrained because they're no longer ISO power. So as they make the chips smaller, they consume more energy. Okay? So that, if you go to talk to people building chips, this is a huge problem right now. So now that's why, you know, everything is limited by power. Data centers is limited by power. Mobile devices is limited by power. And so the whole game is to try to figure out a way around it. Okay, that's all bad news. So why are you working on hardware, Pat? Well, I actually think there's lots of really good news. And this is a graph which I think is all the good news, okay? So this says, so there are different, so this is this little study by Bob Broderson at Berkeley. And he said that he took all the different designs for various types of computers and DSPs and specialized hardware like MPEG decoders and plotted their efficiency, which is how many operations they do divided by the number of milliwatts. So it's basically, you know, energy per milliwatt or operations per milliwatt, right? It's how costly is one operation. And you see our microprocessors that we use are terrible. They're like unbelievably bad, okay? And if you build specialized hardware, and you know, some of these could be FPGAs or GPUs, or if you build like an ASIC, like an MPEG decoder, this is a log scale, okay? So this is like 1,000 to 10,000 to 1. A processor is about the most inefficient computing device you could possibly imagine. Just think about that. A processor is about the most inefficient computing device. It just takes incredible energy to do even the simplest things. But the good news is you could design really super efficient processors or super efficient computing devices. They're not going to look like sequential processors, but there's factors of 10,000 to be gained, thousands to 10,000 to be gained. And so, wow, so even though maybe we'll only have 7 billion transistors, you know, for a little while now, we might be able to build processors that are, you know, much, much more efficient. And that's actually pretty cool because instead of just having one kind of processor, which is sort of nice, because we all get to use the same thing, we can decide whether it's ARM instructions or x86 instructions, but that's about it. Instead, we could build all sorts of things. It'd be sort of like software, right? You know, we can write all sorts of different kinds of software. We don't have to just write one program. If you use software, you could design all sorts of interesting chips. So actually, people are sort of thinking we're actually entering, even though we're ending Moore's law, sort of this golden age of computer architecture, because we can build all these really interesting new kinds of computing devices, okay? And you're starting to see this. Okay, you've all heard about the Google TPU and NVIDIA Turing and so on that are mostly driven by machine learning, but they're all called domain-specific architectures. So, I'm into domain-specific languages. Now we're going to be starting to build domain-specific architectures. This sounds great to me, okay? This is pretty exciting. So, okay. So now if you're talking to people, well, how do they build this hardware? You know? Well, if you go talk to them, it's extremely costly to build hardware. Very few startups in hardware, right? I mean, if you just go, now this is changing a little bit with machine learning, but there's almost no startups in hardware. If you go to, Sand Hill Road, where I live, and you say, I want to pitch a hardware company, the typical thing is, well, it'll cost you $100 million to $200 million to even start the company, unless you can guarantee you can have $1 billion of sales. Don't even come talk to us. Think of that in comparison to a software company, right? You can start a software company in your garage for your friends. It can turn out to be worth billions and billions of dollars. So it's very hard to start it up. And as a result, there's very little innovation, right? We're literally stuck, right? And you think of how little hardware we have to play with, okay? And if you look at what the situation is, it's sort of obvious to me why this is. It's because the software they use to build the hardware is terrible, okay? They have not discovered libraries yet. I kid you not. There's almost no reuse in hardware design. They don't have libc. If you just wanted basic functionality, like a floating point unit, you could just go down to GitHub and get yourself a floating point unit. You'd have to buy some IP from some company, okay? I mean, they have some libraries, but they don't have standardized libraries that are widely used that everybody knows how to use. And they have very primitive programming languages. I'm not going to spend a lot of time on what they use, but they use these languages called Verilog and VHDL, which are very primitive to what you're used to or what I'm used to. So, sort of what got me into hardware is if we could take ideas from programming languages and just software more general, how we develop software, we could probably make this whole thing much easier to do, okay? Much easier to do. So that's sort of what I've been working on the last couple of years. So basically, this is sort of my vision. Okay, so that's cool. So maybe, I don't know, I spend a little time on that because, not most of you are probably software people. You wouldn't even imagine why you'd want to work on hardware, but hardware's fun. If you ever played with hardware, Arduinos, whatever, hardware's fun, and we could really have a big impact on the industry. Even now, we're at the end of more fun. Okay, so that's the first part. Okay, so how do you program hardware? Okay, so you probably all remember this from when you took, some basic computer science course. But how do you think about hardware? Hardware is not that complicated, actually. Okay, the first thing, which I probably all remember, is there's these things called combinational circuits. So this is what's called a full adder. So these are, AND gates and exclusive OR gates. And we have two inputs, A and B, and a carry. So you have 3 bits coming in. You get 2 bits coming out, the sum and the carry. And it's just a little circuit, okay? The circuit, bunch of gates, wired together. And that's called combinational logic. And the rules of the game are pretty simple. You can have any sort of little expression involving these gates. And there can't be cycles in the expression, okay? You can't feed some back into A. There's some cases when you can, but generally you never do that. Okay, there are no cycles. That's a little tricky, but no cycles. So these are pure and total functions of the input, right? Wow, that's great. And also what's cool is those things execute continuously and in parallel. Okay, so all these gates are always computing their things. These gates are realized on the chip, and all the signals are propagating through the wires continuously all the time. So it's fully parallel in space and time. That's cool. That seems like you can get a lot of performance like that. Now, I'm simplifying a couple things. The speed depends on how deep the circuit is, and there's some limit to the fan out, but let's just ignore that for now. Okay, that's the first part. Pretty easy, functional, yay. Second part, well, you need state. Okay, so almost everybody does it this way. When I was in school, they didn't all do it this way, but now they almost all do it. They have these things called D flip-flops, and there's a clock. And when the clock goes from 0 to 1. It rises. The input on D is set in the flip-flop, and it now appears on the output. So if the clock doesn't change, the output is the same. It's always the same. Okay, that's easy. It's called sequential logic. And with those, as you can probably surely imagine, you can build a finite state machine. So sequential logic is a bunch of state with some combinational function. When the clock changes, the state gets updated. Okay? And the only trick, and one thing they do, which is interesting, is they make that clock global. So all the state on the whole chip gets updated at the same time. That's very hard to do. Let's assume they can do that, although it's hard to do. But let's just say that would be great if they could do it. And since it simplifies things so much to do it, they try really hard to do that. Okay? So that's the whole thing. That's what hardware is, basically. I mean, and that's pretty simple. So this sounds like a great opportunity for functional programming, right? In fact, I found out this conference used to be called Functional Programming and Computer Architecture many years ago. I never attended it, but Mary Sheeran, I gave a keynote here. Functional hardware design is a natural for functional programming, and indeed there's been a lot of examples, including some currently developed systems. Clash, MUFP was something that Mary did. Lava, super cool language. There's a bunch of versions of that. And you can go to GitHub, and people are constantly hacking around. These are all in Haskell. And I actually wrote a Haskell program for this talk. So there's a really cool way of doing this, right? You probably all know about it, but I'll just I didn't know about when I started out. But you can just use lazy lists to represent hardware. So if you say something is a stream, which is an infinite list, and you can think of this list as mapping discrete time to some value. So at clock 0, that's the first element of the list. At clock 1, that's the next element of the list. Clock 2 is the next element of the list, and so on. Then you can make a constant with this recursive forever. Right? You just make infinite strings of zeros or ones. You can lift operations onto the list using maps. You have this simple. I probably should say it was a functor, but I can barely program in Haskell. Okay, then. Anyways, then you add this one additional thing called a register, where you give it an initial value and then a string. Okay, so it starts out like the reset value. So when hardware starts, it has all the registers come up with 0, say, and then you can add things to the stream, and then you can write this really beautiful little function in Haskell because you have these lazy recursive lists, right? So TFF stands for toggle flip-flop. So this is just a flip-flop with a not. And the flip-flop just keeps changing state. So it goes from 0 to 1 to 0 to 1 to 0 to 1. Simplest possible state machine. And it's just beautifully expressed in Haskell. Notice the recursion inside the where. Okay, that lets you form the loop there. But it's easy to evaluate because the register delays the calculation by 1. So it has a lazy evaluation is your friend. Awesome. That is awesome. I have to admit, that is awesome. That is awesome. Okay, I'm impressed. Okay, so it's easy to describe hardware. That's all there is to it. That's all there is to it. You can pretty much define any piece of hardware that has flip-flops and combinational functions using what I just showed you. So that's cool. Problem solved. And it even gets better than that. If you look at all these languages that people have worked on, they've had all sorts of other great ideas, like circuit combinators is one of my favorites. Okay, and Kano Elliott, who spoke yesterday, also has worked on this. But if you have a few combinators like fork, join, fold, scan, okay, you can build up more complicated circuits from these simple circuits. Super cool. In Lava, they did this really nice thing with abstract evaluation, so you could just evaluate a Haskell program. So you could simulate it, then you could lower it to Verilog, or you could even lower it to some SAT or SMD type formulas, and then formally verify the circuit too. Right, because it's formal verification has some chance of working in hardware because all you have is these finite state machines. They're relatively simple. It's still not trivial. you know, doing SAT solvers and SMD solvers for finite state machines is not trivial, but, you know, there's sort of a chance it'll work. And then there's embedded DSLs, so you layer stuff on top of it. So this is like all awesome. You guys should be really happy, man. Okay, you hold the key to doing this. Okay. And this combinator idea is, you know, if you think about layering stuff on top of this, if you look at hardware design, I will claim it is the ultimate in staged metaprogramming, at least as I understand it. And even the hardware guys, they call them generators, right? Because think of what you're doing if you're doing hardware design. You have this program, which is this finite state machine that you're running on the hardware. Okay, I just wrote one for the toggle flip-flop. But then you have to write a program that, you know, generates that hardware, right? Because you somehow specify that. Okay? So, and of course that program is run and then the hardware is made. So there's a stage in there called go send this hardware out to be manufactured or go download your bit stream to the FPGA. Okay, but it's a metaprogramming problem, right? And not only that, hardware is just programming. I mean, it's sort of obvious, but it's like, you know, some people think like hardware design is something different than programming. I've been building a lot of hardware on FPGAs, and I'll talk about a chip I just taped out later, but I just feel like I'm programming. You know, it doesn't seem any different. I just write these programs that generate hardware, which is another program, and I'm just programming. It just feels very natural to a programmer. So there's all sorts of, so this is sort of, you know, maybe obvious, but it's sort of useful to think about that, I think. And there's a bunch of stuff, there's some stuff that's going on here that you may have heard about as well. So there's a language called Chisel, which is embedded in Scala. Okay, and these are called hardware construction languages because they have a little core, sort of like that TFF example I showed you, a little core sort of hardware language. And then they have a big, you know, another more complete programming language around it, Scala or Python, in case of Magma, which lets them metaprogram the hardware. And so we've been working with the Chisel group on doing this, and we have a Python version of just because we found that a lot of hardware engineers are just comfortable with Python, but here's an example of some simple circuits. So, but you can pick different ways of doing it. Okay, that's cool. So that's really good. So that functional programming, metaprogramming, very good. Okay. Still have to convince them to use it. That's another problem, but okay. But what I want to spend less of time on is this is too low level. This is too low level. It will be too hard to build hardware at this very low level of abstraction. In fact, if you're a hardware designer, they would call this like structural Verilog. It's basically you take circuits and you wire them up. So, you know, it's not bad, but it's just fairly low level. It's considered very low level. So they want to, if you, even Verilog and VHL, they tried to raise the level of abstraction. Okay, so how could we even do better than this? So I'm going to say there's two stages to this, maybe mid-level abstractions. So what's the next logical steps from this to higher level abstractions, which is maybe what we'd really like to be able to do. Okay, so mid-level abstractions. So how can you do a little bit better than just circuits and wiring them up? Okay, well, here is an example of how people program in Verilog. So they have this thing they call behavioral RTL, behavioral register transfer language. It's sort of a weird language. Like so first of all, you'll notice instead of equal signs, they have less than equals. That means that those are concurrent assignments. So all these less than and equals are all happening in parallel, but they're inside this imperative-looking code, like this case statement or if-then analysis, and they can even put loops in here. But the imperative code sort of gets predicated, if you like, right? In other words, what actually happens is this gets turned into a parallel function where say like that ur._tx, it's assigned to in 3 places, but only, you know, there's some kind of like select going on in front of it, which decides based on the conditions of X state, which of the values actually gets assigned. So it really is still functional, but they like to write this imperative code. Also, you see this X state equals X state plus 1, okay? So all the values of X state on the right-hand side are the previous values of the state. So X state is a register. All these things are registers, by the way. And then it gets updated. So all the values of all the variables on the right-hand side are all fixed, okay? But then at the end of this, you update all the values. Oh no, I'm having trouble explaining this because being a sequential programmer, it just sort of makes me uneasy writing this kind of code. I hope it makes you uneasy too. Very error-prone. Sort of a combination of imperative programming, concurrent programming, and functional programming, all mixed up together, and you can get very, very confused when you write this stuff if you don't really understand what's going on. But they do this. This is what they call behavioral specification. So when people use Chisel or they use Magma, the number one complaint when we give those to hardware designers is, wait a minute, I'm used to writing this. I want you to write that. Okay, so anyway, it's not that hard to allow you, to transform this kind of program into one of those, so you can do it. But I just want to show you, that's an example of how they try to raise it up. The other thing that people try to do, is these little programs here are finite state machines. By that, I mean that they might, like so this is actually, you may recognize this if you've ever played with an Arduino, this is actually a UART. This takes a byte, which is in TX buffer that has 8 bits, and sends it out sequentially over the wire UART TX. So it's a little finite state machine, right? It starts out in state 0 and it counts up, and it sends out a 0 in the first bit, start bit, then it starts sending out the data, and then it sets the stop bit, and then it stops. I haven't shown the whole thing, but it's a little tiny finite state machine. So a lot of times in hardware, you're making these little finite state machines, and they have a start state and an end state, and then they execute this little program. Okay, so you can do this cool thing. Another great idea, I think, from the functional programming community, is you can build a little set of finite state machine combinators. And this particular example came from the system Blarney. Pace is another example. BlueSpec, which I haven't talked about, also has something called statement FSM. But you just sort of say, I'm going to make these finite state machines. I'm just going to combine them. So I can sequentially combine them, I can combine them in parallel, and so on. That's sort of cool, because now you can write these fairly simple little programs. They're simple. They're not recursive programs or whatever. But you combine state machines like that. So this is not very widely used. And BlueSpec, people using BlueSpec do this all the time. They don't typically do this when they use Verilog or VHDL. But it's a neat idea. I use it all the time. So I can just build up little finite state machines with these little combinators. And so that works pretty well. That's cool. Another good idea. One thing we've been doing a lot to try to approximate this is to actually use coroutines. So again, we're in this, less elegant language. This is Python, but we just write coroutines, and then we analyze a control flow graph and convert this to a finite state machine. But you could think of the statement things like whiles and ifs and else's as combinators. So you transition from yield state to yield state through the control flow graph, through these combinators, which give you the semantics. So anyway, you can sort of get approximate little programs using this technique. And for things like this UART, works really well. Just, so much easier to write a little tiny program that has that finite state machine than you get the hardware. Okay, so I think we sort of know how to do this kind of stuff. Okay, but we want to go higher level. Okay, so what might that involve? Okay, so if you go to talk to everybody that seems to be trying to convince people, like particularly FPGA vendors, but even the ASIC vendors, they are all excited about what they call high-level synthesis. Okay, so and this is an idea that's been around. I remember when I was in grad student, hearing about it. It was sometimes called Sita gates, right? They sort of love this idea of, could I write a C? I think the vendors like it because they basically think, we should make this like software, so everybody knows C. They're all low-level system programmer types. So if we could just compile C into hardware, they would love that. That would be like a panacea, okay? And there's various versions of this, but it's all sort of the Sita gates is a good way of sort of capturing the vision. Like I can take like a C program and compile it into gates. Okay, sounds good, but it just can't be done, okay? And, it doesn't mean there aren't a few systems out there that do parts of it. They can have certain dialects of C. You may have heard of System C, other things. But why is this really hard? I think it should be obvious to everybody here why it's hard, but let me just sort of state it as precisely as I can. First of all, if you have C, it's this imperative programming language, you have to automatically parallelize it, right? You have to completely parallelize. In fact, it has to become completely concurrent. If you don't parallelize it at all, it's going to be the most unbelievably inefficient hardware you can imagine, right? Because you have these 6.9 billion transistors you got to be running on in parallel, right? When you have finite state machines, if you're not running the finite state machine, the hardware's just sitting there doing nothing. So you don't want to do that, okay? So it's hard to parallelize it, okay? And that's a huge problem, right? Automatic parallelization, huge problem. Maybe they can parallelize loops, they can parallelize a few things, but in general, they can't automatically parallelize the program, and so it doesn't work. Now, you would think, so here's something, there hasn't been a lot of work on this. Can you really do high-level synthesis of a more functional programming-like language, right? So you'd think you'd have a lot of advantages to that because you don't have to worry about all the imperative stuff going on. So that seems like it needs more work. Maybe there's work I don't know about, but there might be some hopes for that. But in general, even with all these Haskell-like systems, they don't take arbitrary Haskell programs and compile them to hardware, right? They have this little embedded language that they compile to hardware. So taking an arbitrary program, compiling it to hardware is hard. Okay. The actual tricky part, and this maybe isn't so much a PL issue, but more of a compiling issue, you actually have to generate efficient hardware. It's maybe a little bit related to automatic parallelization. So there's two versions of this problem. One is I could give you the hardware, and I could say, given this program, compile it onto that hardware. So we're really pretty good at that, right? Because that's what we do when we have a normal processor. We take the processor, and it has a bunch of hardware, say instruction sets, and the resources are given to us, and we decide how to use them. Okay, but and that can be a hard problem, right? Compilers are hard. There's all these, NP complete problems in compilers. Okay, and an example of doing that is synchronous data flow, which I'm not going to talk about. But they formulate the scheduling problem as an IOP problem, and they run it. It's a hard problem to solve, but they can sometimes map it to the hardware. So okay, that's part of the problem. But there's another problem that's interesting. Is let's say I don't tell you what hardware you have. So like, how many adders do you have? You can pick whatever hardware you want. You could take some parts of the program and say, I'm going to make that hardware. And I could take some parts of the program and I could say, that part's going to reuse the hardware I already have. So you have this one extra level of deciding what hardware should I actually make. And that's very hard, too. That just makes the whole problem even harder. Okay? So this is a hard problem. These are hard problems. By the way, very few people right now are working on these general HLS problems. It's sort of amazing. There's only a couple people I know in the world working on it. It's a hard problem, but this vision without some more people working on these kinds of problems will never be even closely realized, right? So how do you, and it's probably more of a compilation problem, but it's important to be able to compile this stuff. Okay, so I hope somebody works on that. I've actually started to dabble in it a little bit, but it's a hard problem. Okay, so there is a way to make some progress, which is DSLs, right? So I think Kunli talked maybe, I don't know, here, who one of my partners in crime at Stanford, about using DSLs for parallel programming, right? And you know, the whole argument for why you should use DSLs is you could not build a general purpose parallel programming language that could automatically get compiled to lots of different hardware, right? So you know, and I should mention in this version of DSLs, performance is really important, right? Not only do you want to have the semantics of the DSL, you also have to be able to compile it. And the DSL argument at the time, you know, is, you know, that you have this higher level of semantics, so you have all these program transformations that you could do at that level besides the lowest level, which is good. Like matrix multiplies, for example, you can figure out how to do those optimally. You know, you can restrict the programming language, right? You can both make the computations less general, and you can make it easier to analyze. You know, often analysis is making it easier to analyze is as important as you know, restricting the computation. But there's a trade-off there, right? You can also add features to make it easier to analyze. And the other thing you do is you say, I make a DSL in an area where people have worked on it a long time and they know how to parallelize it, right? Like, you know, linear algebra. They've just worked on linear algebra a lot. You know, they've worked on signal processing a lot. They know how to map it to hardware, and there are good heuristics that always work, and you can do it robustly. So to me, that's what the argument for DSLs and parallel programming is. I mean, and it's not all bad. I mean, it's a less general language, but it's also domain specific. So if you match the domain of your users, they're going to be super happy. But it's also, you know, sort of works, right? So it's tractable. It'll work. So I think this will work in hardware, just like I think it has worked pretty well in parallel computing. Is you build these DSLs that help you raise the level of abstraction, but you've restricted the domain. So it seems like a fairly good approach. So in our hardware system, we've been using this halide one, which I just also mentioned because there's this history of you know, functional programming on images. Again, Connell Elliott's worked on this and others, but it goes way, way back. I mean, first time I saw this was a system called Pico at Bell Labs. When I was at Pixar, I actually worked on a language called Pimple, called the Pixar Image Processing Language. It was a fun little system. But anyways, Pimple was my language. But anyways, you know, the idea of this is you write out your image processing operations as functions, pure functions or functions, and then you don't worry about specifying how they're computed. Okay, so you have this declarative specification of your calculation. Now, halide uses discrete values for coordinates, so that's an interesting issue. You can talk about that. But this is an example of a convolution. And it also has these things called reduction domains in it, which lets you sort of, it's like a tensor summation thing. And in fact, halide is being used a lot in machine learning right now because by doing these contractions, you're able to do arbitrary tensor calculations. So you really have an n-dimensional, it has an n-dimensional image, and you can contract along any dimensions using these simple kinds of expressions. Okay, so that's nice. But halide, you know, if you've been following this work, halide did one other neat thing, which is you specified your calculation, but you also specified the schedule, what's called the schedule. So you could think of this as like a high-level set of compiler directives that you now call. So these functions that you're computing, you're given compiler directives to those functions that tell them how to sort of compute themselves. So I'm not going to go into all this scheduling language in detail. You can read the halide papers on that. It's a little complicated. I don't think it has a completely precise semantics either, but you know, the first one you just mentioned, where you're sort of saying you're going to compute this output image, but you're going to tile the result into 64 by 64 blocks. But what you can do with this, so halide schedules can be you know, Halide is being widely used for doing imaging right now, and it has pretty good schedulers for software. So you can schedule it on GPUs, you can schedule it on CPUs. And by the way, the schedules for different devices are very, very different. There's been some most recent work on auto-scheduling it. So given some space of schedules, can I solve for, you know, the best schedule? It's somewhat surprising that even in this restricted domain, that's a really hard problem. It's not been worked out in general, but they're starting to have good heuristics for auto-scheduling it. So that means you wouldn't have to write out the schedule. So what's sort of nice about this approach is you start out with some way of generating schedules, you get experience about what works, and you try it on a bunch of hardware, and then you look for an algorithm to make it automatic. But what this example shows is you can take the Halide scheduling language and tweak it a little bit so you could create schedules for hardware. Okay? So schedules for hardware would be like, oh, by the way, I'm going to declare what resources I have, like I have so many functional units, and I'm going to say hook them together in a pipeline. I'm going to say make a memory of a certain size. And this thing actually creates a schedule that creates this hardware. So it creates a 3x3, you know, set of multipliers that form the convolution and produce a product. That's all parallelized in hardware. It creates this data structure called a line buffer, where you can stream data into the line buffer, and it keeps track of adjacent rows. And so when you can read those all out. And anyway, so this is sort of, you can think of this as a space-time schedule, right? It's a schedule, mostly Halide schedules involve time, do this and then do that and then do this. This tells you, no, also create these resources, put them on the chip spatially, and then sequence them together in time. So it's sort of somewhat similar concept. So anyway, that's just interesting. So that's been the approach we've been taking in a lot of our applications, is sort of take a DSL, investigate how to map it, you know, through these like scheduling like operators into hardware really efficiently, and then try to generate the hardware. So anyway, there's not a lot of work on this, but I think there's opportunity to do a lot more. I could imagine a bunch of DSLs, just not only for certain application spaces, like imaging and signal processing and machine learning, but also for building hardware itself, okay? So, you know, we actually have a bunch of different sort of, I would call DSLs that we're using right now for building different types of hardware. So, anyways, I'll just mention those and go look at our web pages and so on. I will mention this one that I'm particularly excited about, which goes back to an old paper by Gordon Bell and Alan Newell, which is two DSLs, PMS and ISP, for specifying processors. Maybe I'm running out of time, so I'm not going to talk about this, but they wrote this book called Computer Structures, which is a really great book. It's an old book, but it was written in the era when we used to have lots of different kinds of computers. And this book was sort of like, it's like almost like a, you know, biology book. And here's all the different kinds of computers we've built. And Alan Newell, of course, who you knew was really into like notation and DSL, decided, you know, Gordon Bell was the actual architect, right? He had built the PDPA. He said, let's invent a notation for specifying computers. And I'll just include this, but you can't read this. I have it on my laptop. I'm just going to skip over it. But this is a complete specification of the PDP-8. So this book has chapters where they describe various architectures, and then they have this DSL that says, here's what this architecture does. It's sort of like a little bit like a manual, right? If you ever read like the ARM manual, you have all these instructions, and here's what it does. This thing, if you look at this DSL, it has what is the state of the processor, how do you decode the instruction, and then what happens if you match the instruction. Sort of a cool thing. Whoops. So anyways, we're actually trying to do this at Stanford. Actually, I just taped out my first chip a couple of months ago. Yay. 16 nanometer process. It was very painful. The tools are bad. Believe me, the tools are bad. Believe me, the tools are bad. Okay. But we built what's called a coarse grain reconfigurable array. Okay. It's like an FPGA. It has a network of switches. And then there are these islands which contain processors. And in a coarse grain reconfigurable array, these processors, you think of them as like ALUs. Okay, so each of those gray blocks is, think of it like a RISC-V ALU. Okay, and we built the smallest chip that we could possibly build, is like 3 millimeters squared, because we really haven't scaled this stuff up. But even then, there's room for 10,000 ALUs on a single chip. Okay, so that just shows you how much 10,000 essentially RISC-V ALUs on a single chip, all connected together like this. And this is something that you could imagine building. But we built this using these kinds of techniques where we have various libraries and DSLs for creating interconnection networks, memory structures, processing elements, and then combining them all together in a chip. So that's the end. Just summarize my whole thing. You know, even though Moore's law is ending, we're actually in this really exciting time. We have all these transistors and all this hardware resources to build, and the key to really making more efficient computers is to build more interesting hardware devices. Call them domain-specific architectures. There's huge markets for those in things like machine learning, other applications. Hardware design is just like software. You know, there's a few different abstractions, like combinational logic, you know, flip-flops. There are additional things if you go down to the physical level that you have to learn about, but a lot of it is just like writing software. If you like to program, you can program hardware. The current hardware programming environments, to me, are just terrible. It's sort of unbelievable. Verilog, VHDL. I mean, they're not like, they're sort of like, you know, I don't know how to, it's like before we had C, like you had B or something like that. You know, you weren't even, you're not even there yet, okay? And they really aren't evolving very much. You know, I think you could reinvent a whole set of languages, sort of like I was describing. This community's already done groundbreaking work in this area, but you need to go higher level. You can't just do how you represent basic hardware. You need to go to more like high-level synthesis and domain-specific languages. And then, you know, it would be really cool if we could just sort of be writing some program and say, this part of it I want to put in hardware, this part of it I want to put in software, and make that just really easy to do. And I think that's actually something, as a community, we could solve, or could at least aspire to solve. And believe me, I'm an amateur. You should help me do this, because I do not really know what I'm doing. Thank you very much.
Thank you, Pat. So we have questions from the audience.
Okay.
First one's from Ed. Why would you verify a Verilog using SMT SAT instead of verifying using theorem proving and verified computing to Verilog?
What,
So I think it's a, yeah, so now let me try to interpret the question a little better than just reading it. So I think it's a question about the approach to verification. Why would you take the Verilog and try to verify that as opposed to using theorem proving? I think maybe the question is about starting with a higher level language.
Yeah, and I didn't mean, so some people try to verify in Verilog, but you can certainly try to verify in the higher level language. I think when they did it in Lava, I think they verified it, you know, from Lava directly, not from the Verilog. We do some verification. We generate an IR, and we verify from the IR. So we convert to an IR, and then we verify from the IR. Okay. Yeah, you want to verify at a higher level if you can, definitely.
All right. And verifying the program as opposed to the transformation process, is there any issue there? Oh,
yeah. So that's an interesting issue. You know, verifying the transformation for all possible inputs is a much harder problem.
Okay.
They generally don't avoid that. They don't try to do that. They will try to do something where if you do a particular transformation, that the thing you transform to is sort of equivalent to what you had. But they have trouble. I mean, I think it's pretty much an open problem, is if you have an arbitrary generator or an arbitrary transformation, can you verify that for all possible inputs? But you can certainly verify that it worked in this particular case if you can verify that the two circuits are equivalent. So that's one thing about verification in hardware that I didn't quite realize until doing this, but they have this circuit equivalence thing, and that's pretty robust and useful technology. So if the two circuits are equivalent, they always compute the same things, you can at least verify that pretty easily.
Okay, on a different topic, what do you think about synchronous data flow programming languages for hardware design?
Good question.
Like synchronous Lucid.
Actually, I was anticipating that question.
That's what we call an excellent question when you have a slide.
Actually, what's the question? Oh, you can. Oh, all right. That one I was actually. Was I not have it in here? Oh. Hold on. I'm not going to show you that. But let me just say, okay, so there's another way of doing this, which I'm super fan of, called data flow. And data flow is a little bit different than what I just said in that you basically put a filter on things. Okay, so you add one more operator where you can sort of conditionally filter a string. Okay, and merge two strings together. So it's actually very simple. You add two functions to Haskell and you get data flow. Okay, the problem with that is you need unbounded FIFOs between all the streams. So the streams might just get way ahead of each other. They're not all in synchronous. And synchronous data flow says, I'm going to require that all these streams, these functions, take sort of K inputs and produce, say, L outputs. Okay, so there's some, rate restriction between the two. And that lets you statically schedule things. So yeah, that's a really useful operation. That's not always efficient, and there's still issues if you might want to include FIFOs. But we, in the stuff we're doing with the scheduling, auto scheduling in hardware, we're using ideas from synchronous data flow.
All right. So this is a kind of a practical question, an adoption question. So the usual problem, how do you get things adopted? Matt asked, the main issue for mainstream adoption of Verilog is the language to bit stream flow requiring traditional HDLs. They reference them for debugging, rely on them for debugging, timing optimization, interoperability with vendors' IP. Do you have any ideas on?
Yeah, so I think interoperability is a huge issue, and in this particular community, there I think somewhat resistant to change as well. So I mean, it's a particularly big challenge there. There's a bunch of things going on. One is people are building a lot more hardware, and one of the really interesting things, we've got a bunch of funding. A bunch of people that are building hardware are more like systems companies, like Google and Amazon, Facebook, and Apple, not sort of traditional hardware companies like Intel and NVIDIA. Some of their hardware teams, it's sort of fun to talk to them. They're immersed in this big software, machine, right? And the software guys don't like the way the hardware guys build the hardware. So they're getting there's a lot of discussion in these companies about how we should do it, and they seem to be pretty open to ideas. So there's some possibilities that they'll try new things. For example, in our tools, we're hoping that Facebook is going to use them in a couple of big projects coming up. So I think they have this issue of like lack of productivity, and they want to start designing things quicker. But it's a huge problem is getting adoption. I wish I know the answer to that. It's not going to be easy. I think a lot of things we do with language interoperability and library and reuse can be applied in this area, but I don't know the answers to all those questions. If you have ideas, come talk to me.
Right. So back on the programming model, William Benjamin asked, have you thought of parallel hardware as Petri nets instead of FSMs?
I've thought of parallel hardware as Petri nets. I mean, I don't really have a strong feeling about one versus the other. Maybe somebody can inform me about that. This particular model I showed with these lazy streams or stuff worked pretty well, and then the data flow, I'm used to the data flow, but Petri nets I know is another good possibility.
Okay. Well, let's try one more. Phil asked, you referred to Moore's law. The empirical evidence is clear, but is there some reason why it has to be?
That it has to end?
Yeah, that it has to hold, or
has to end or has to continue? I mean, first of all, it's not in the law, right? I mean, somebody had you say that this is what we're trying to do, and they had to invest in it, right? If you go talk to Intel, they'll say, Moore's law just doesn't happen. We have to spend a lot of money to make it happen. Actually, one of my slides here is the announcement from TSMC that they're about to invest $25 billion in their 5-nanometer fab, okay? And I have a picture there of a particular EUV machine which costs $125 million for one of these machines. So Moore's law it wasn't for free. I mean, maybe as a programmer we thought it was for free, but for the people building the chips, it was not for free. This is a very expensive thing to maintain, and a lot of the rate is governed by how much it costs, and how much money they have to invest in it. So in that sense, Moore's law is not a law. But with the right investments, they were able to continue this transistor doubling. The end of Moore's law, I think, pretty much everybody agrees on. You know, the only thing they might argue is, will there be some replacement for it? Well, like we switch to some other type of transistor, and you know that might happen. Maybe they'll come up with some fundamentally new different way of doing it, but that wasn't the case with Moore's law as we've grown used to it. It was a very systematic re-engineering of the process to increase the density of devices. So that's definitely coming to an end, and you know, we'll see. But you can read the press. You know, David Patterson, John Hennessy, they just won the Turing Award. Their talks are basically about the end of Moore's law, and I think there's not a lot of people doubting it.
All right. Well, thanks for lots of food for thought. Pat has punted it back to you now. He's asked for help, so it's on you, and he'll be around all today. So let's thank Pat one more time.
Thank you.